I want to talk about what I'm going to call the formal definition of a graph. After we've talked about all these examples, come on. I don't know if you really get this feeling, but you should at some level get the feeling that maybe it's not clear exactly what we're talking about here. I keep on saying that like the graph is important, but actually what the edges specifically look like, the geometry, is not important. You should ask yourself then, okay, what really is important? Or what even is the graph? I said at the beginning, I didn't really tell you what a graph is. I just said a graph is something which looks like this, right? That's a graph. But then later on I said actually the shape of the edges isn't really important. You should say, well then what are you talking about then? If you just drew me a picture and said that's a graph, but then you said that the picture doesn't actually matter. We have to have a real definition, a formal definition. Mathematicians do not like to just point at a picture and say, that's what I'm talking about, because that's not specific enough. You need to say in some kind of formalized language exactly what you're talking about. Here's how we do it for a graph. What matters is not the picture. The only thing that matters in a graph is what are the vertices and what are the edges. Where do the edges go from and to? All right, so here is how we are going to... What is a graph really? A graph is a set of vertices together with a set of edges. A set of vertices together with a set of edges. For example, a graph which I would informally just draw as a picture like this. Let's say it has something like that. And I'm going to call these A, B, C, D, E, F. All right? Those are the vertices, okay? This graph, formally speaking, is not a picture, because the picture, as I've said many times, the picture itself is not really important. What's important is what are the vertices and which ones are connected to each other. The formal description of what this graph is, the graph is truly, its true nature is not a picture. Its true nature is a set of vertices together with a set of edges. And we write it this way. The vertices... As a set in mathematics, when we write a set, you use this curly bracket here. And I'm just going to write out what the vertices are. They are A, B, C, D, E, F, right? Those are the vertices. And then the edges is another set, only this time the edges, I'm going to indicate them as pairs. So this edge right here from A to B, I'm going to write as the pair A comma B. That's the first edge from A to B. And then I also have the edge from B to C. You just have to write them all down. Then I have C to D. These are pairs. Then I have D to E. I also have, I'm going to go down here because I'm out of room, E to A. And finally, one more edge, E to F. All right. That is the true nature of the graph. This picture is a helpful representation of the graph, but that's not really truly what the graph is. This is what the graph is. It is a set of vertices together with a set of edges. Now, typically we would write the whole thing as a single giant pair. I would write it this way. G equals, so G is like the name of this graph. I'll call it big G. And what is it? It is this set A, B, blah, 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 to F. I write the vertex set first, comma. Now I write the edge set. The edge AB, the edge BC. I just write this stuff again. You get the idea? The edge E to F is the last one. All right? And then I close. This is a big pair of two sets, right? You got to have all these various brackets and parentheses in the right place, or else it won't make sense in the way that you want it to. Okay? This is the true nature of the graph. Why am I saying anything about this? It's because this is how mathematicians truly think about the graph. We don't think of it as a picture, although we sort of feel in your heart like it's a picture, and you often do have a sort of working image of it in your mind as a picture, but really its true nature is this. It's just a pair of sets. All right? we can go back and forth. So here I started with a picture and wrote down the formal description. We can also go the other way around. Start with a formal description and draw a picture of it. Let's try one like that. This would be a typical homework problem. How about draw the graph? And then I will just give you, say, some graph, which is, sorry, a pair. Every graph is a pair of two sets. So the parentheses begins the first pair, and I'll write the first set. Let's say in this graph it's A, B, C, D, and then the set of pairs is going to be, these represent the edges, AC, BC, AD, CC, BD. Like that, right? So we have a pair. The G overall is one big pair. The first thing in a pair is a set. The second thing is this other set of pairs. So this is a little confusing. You've got to get all those brackets in the right positions. All right. Can we draw this graph? Yes. So you just look at this and you realize these things represent the vertices. So there are 4 vertices. They're called A, B, C, D. So I have no idea what it's going to look like, but I might as well just sort of put them in a square like this, I guess, because there's 4 of them. I'll call this one A, this is B, this is C, this is D. All right. And then I draw in the edges as they are listed. So there is an edge from A to C. Okay. There is an edge from B to C. All right. There's an edge from A to D. It's here. There is an edge from C to C. So I guess this is like one of those looped edges, right, from C back to itself. And there is an edge from B to D, like so. All right. That's a picture of the graph. And I will have you know, this picture is correct. This is a picture of the graph. Or another way you could have done it, what if, I wrote A, B, C, D kind of in this sort of clockwise manner. What if instead of putting them in this arrangement, I put them in this arrangement? I don't know why, but maybe I put them this way. A, C, B, D, like that. Yeah, okay. This description doesn't say where the points are. It just says their names. It just says there are 4 points. They're called A, B, C, D. Then I connect up the edges like before. A to C, B to C is like that. A to D, C to C is a loop here. B to D is here. All right? These look different, don't they? I'm here to tell you, though, they are the same graph. All right? They are the same graph. They look like they're different, just they are different representations, but they represent the same graph. They have the same points, the same vertices, and they have the same edges connecting the vertices. So they count as the same graph. So these are both correct. And you could write these points in any arrangement that you want to, and it would still be the same graph. I thought maybe we should talk a bit about the historical beginnings of graph theory. Graph theory, as we now know it, began in the late 1700s. It was kind of a late addition to the pantheon of mathematics. But anyway, it was the first person to really identify this as a new thing was a mathematician named Euler. It looks like Euler, but don't say Euler. You'll sound stupid if you say Euler. It's Euler. This is a German name, so it's pronounced Euler. Anyway, Euler was studying a problem. This is not like a very serious mathematical problem, but it was something that people would kind of casually chat about, and it's called the bridges of Knigsberg problem. This is a place. Knigsberg is a city somewhere. I don't know where it is. This is like the late 1700s that Euler was around doing his business. Euler is, one of the greats of all time. Like, for example, the number E. You may be familiar with the number E. It's named after Euler. The E stands for Euler. Euler was studying this problem. Here it is. Apparently, the city of Knigsberg had like a river going through it. Right through the city is this river. And here's land on the top and on the bottom. And the river had these 2 islands. So I got 2 islands. And these islands are connected to the land on either side of the river by bridges, and the bridges went this way. There was a bridge here, another bridge here, there was one going across, one going here, one going here, and then two here also. All right? This is the scenario for the bridges of Knigsberg problem. And people wanted to know, can we walk across all 7 bridges without repeating any? This is the question. You can start wherever you want. Can you walk across those bridges? Hit each bridge one time, but don't repeat any of the bridges. All right? Is it possible? And some variations of the questions would say, can you start and end at the same point while doing this? That would be, I guess, maybe harder. I don't know. Can we walk across all bridges without repeating any? And then furthermore, can we do it and end where we started? All right. I would just like us to think about this problem a little bit. This problem seems to be a geometry problem, right? Because it looks like I got shapes here that are, they have these, blobby things and lines between them. And the question I'm asking is about the picture somehow, and so it seems like you should be doing geometry when you solve this problem. But I will have you notice, the traditional tools of geometry actually are totally inappropriate for a question like this, because the traditional tools of geometry would have you looking at distances or angles. These are like the basic things that you study in geometry. Straight lines, parallel lines, angles, all that kind of stuff, all right? If you think about this problem, actually none of that stuff matters. Whether these, for example, whether this bridge is straight or is it curvy, like when I drew a slight curve there. Of course, there's no reason, probably the real bridge was really straight. But it doesn't matter either way. What exactly, at what angle do these bridges meet the land on either side? These questions are completely irrelevant to answering a question like this. Can I just cross every bridge once? All right. This seems to be a geometry problem, but actually it is not. It is it's a problem about graph theory. All that matters here is that you have certain locations that are connected by bridges in certain ways, right? Actually, this problem right here, we can translate directly into a graph. I'm going to try and translate this problem here into a similar question about a graph, all right? As a graph, these bridges are each going to represent an edge. Now, what are the vertices of the graph going to be? Well, the vertices would represent the various land masses which are connected by these bridges, right? So I'm going to have one vertex for this island over here, which is going to be connected. I guess this one will have 5 connections coming out of it. Another one for right here. And here's the interesting idea that that Euler had, was that this entire top landmass here, you might as well consider it to be just a single vertex, because all I care about in this problem are the bridges, right? When you cross a bridge or do not cross a bridge. There's nothing in the problem about walking around on the top, right? I didn't say anything like that. So apparently, while you're crossing all the bridges, you are allowed to walk around on the top bank however you like, all right? What that means is, in terms of the setting here, you might as well consider the entire top bank to be just one point, right? Because all locations on the top are regarded as equivalent in this math problem. And similarly on the bottom, right? You might as well consider the entire bottom bank to be 1 point, because there's no restrictions on how you can move about along the bottom bank. All right, so as a graph, it's really just this. We have the 2 islands, we have the land on top and the land on the bottom. Those are the only locations that matter. And then these bridges, each of them becomes an edge in my graph. So I got one there, I got one here, that's this bridge here, going from the island on the right down to the bottom. Then I have one going up, that's like that. And then I have these two here. They will be two edges like so, and then these two here will be two edges like so. All right. As a graph, it's this graph right here. And now the question becomes, we translated the original picture into a graph. We should also translate the original question into a graph. The original question was, can I cross every bridge once without repeating them? As a question on the graph, this now is a question about paths, right? Can I go, around the vertices here? Can we find a path using every edge in the graph exactly once? This is the question that I just said in terms of the bridges. I said, can you cross every bridge without repeating any? That's the same as this question. Can you find a path in this graph using every edge exactly once? Exactly once meaning one time, not like one or more, not one or less, but exactly one time. All right? Can we find a path? And then I said there was another, related question. Can you do it and end up in the same place where you started? Well, that's another word that we talked about. That would be, can I just say, or can we find a circuit? Remember, a circuit is a path which begins and ends at the same point. Can we find a circuit using every edge exactly once? All right. Euler translated the original picture into a picture about this graph, and then Euler invented a bunch of fancy, actually not too fancy, it's not very hard once you think about this properly. Euler invented a bunch of mathematics for studying diagrams like this, which is now what we know as graph theory. Of course, Euler wasn't the only person to invent things in graph theory. People are still, people still research graph theory today. Anyway, these are the questions. Actually, these questions became so interesting to other people in other scenarios that there's a name for them. This thing is what we're going to talk about first. A circuit using every edge exactly once. There's a name for that. I'll just write a little definition here. A circuit using every edge exactly once is called an Euler circuit because of Euler's role in developing the history of this kind of mathematics. It's called an Euler circuit, a circuit which uses every edge exactly once. It's called an Euler circuit. Actually, Euler, this original bridges problem is kind of that wasn't really important for anything. It was just sort of a what we might call a recreational mathematics problem. But actually, Euler circuits can be important in the real world. Let's just try something like that. All right, this is not exactly a real world problem. This is a made up problem, but just to give you an idea of why Euler circuits actually are sometimes of interest in the real world. Let's consider this graph right here. And let's imagine that this describes a grid of streets where you can, there's just these streets in this arrangement, all right? And let's say we are thinking about the snowplow guy, all right? Let's say right here in the middle, I'll put the star there. This is where Mr. Plow lives. Mr. Plow lives here, all right? The guy who does the snow plowing. And let's say, as Mr. Plow, this shouldn't be a surprise to you. Let's say Mr. Plow wants to drive along each street here only once, right? To plow all the roads. The question is that possible? Actually, the question is the same as the bridges problem, really. It's about, can I cross each of these edges one time? And I guess the ideal situation would be for Mr. Plow to return to his home at the end. So, here's the question in this setting. Can Mr. Plow plow each road without revisiting any? and end up at home. Is that possible to do from here? I don't know. I mean, we're going to talk about, actually, once you know the trick, it's very easy to answer this question because Euler proved a very fancy theorem that tells you immediately whether or not it is possible to do this kind of thing. And because I know the theorem, I can say immediately, no, it is not possible. Just by looking at the graph here, you can tell if you know what to look for. It's very easy to tell. It is not possible to do an Euler circuit. So this question here is really the same as, is there an Euler circuit? Starting and ending at the star, right? These are equivalent. All right, this kind of thing, this is a made-up example, but you can imagine there are situations in the real world where real people might actually want to do this. For example, if you are in charge of the school buses and you want to design routes for the school buses to drive so that they can pick up all the kids, but they don't need to do any extra driving, like they don't want to drive past the kid's house twice, because wouldn't it be better if you could just sort of hit each street exactly one time without repeating any of the streets, right? Or if you wanted to have a parade go through town and visit every street once, but you don't want to go back across the street you already went across, is it possible to start the parade and finish it here, but hit every street only one time and not repeat any? Actually, in this case, that's not possible, but these are all sort of real-world scenarios in which that kind of question would arise. All right? All right, here is a graph, and I'm going to give names to the vertices. Let's call them A, B, C. That's a C right there. A, B, C, D, E, like so. All right. This one, just by looking at this one, can you tell me if it has an Euler circuit or not? Does it have an Euler circuit? Here's the question, does it have an Euler circuit? Well, in this case, actually, the answer is yes. And when the answer is yes, actually, it's not so hard to figure it out. I mean, just by sort of trial and error. Let's say I'm going to start at A, and I want to hit every edge here exactly one time. Let's see here. So the answer is yes. Here it is. A, let's see, I'm going to try and do this. We're going to have to talk a little bit about how exactly do you do this, but I already know the answer here. Let's just see if you agree. A, B, C, A, D, E, B, E, C, D, A. How do you think about that? How do you think about that? This is an Euler circuit. What it means is you start at A, and then I'm going to try and describe how you can hit every edge one time, no repetitions of edges, and end up back at A. See, it goes A to B to C to A, then D, E, B, E, C, D, A. I think that hits every edge one time. Can we, I'm going to try and draw this path on the picture so that it's easy to see. Can we all have a little art lesson here? This is a little tip to make it so that you can draw the picture in a way which is actually comprehensible after the fact. Check it out. Here, I'm going to make this same picture but bigger, just so we can practice a little drawing lesson here. Please draw it so that I can read it. Sorry for the squeaks. A, B, C in the middle, D, E. All right. I'll show you first how to not draw this. Here's something, I don't know why, but I see a lot of people. Maybe I do know why. Here's how not to draw it. A, B, C, check it out. I go, all right, first from A to B, then from B to C, like that. Then from C to A, like, so C has a point there. Then from C to A, like this. Then from A to D, like this. Now, you could go that way or this way. I guess I'll go this way. It actually doesn't matter. Then from D to E like this. Check it out. I said this is the wrong way to draw this picture. Why is that? What you end up with is just a bunch of arrows on the edges, which gives me no idea where you're actually going from one point to the next. For instance, when you start at A, where do you go first? Do you go to B or do you go to D first? Now, because I wrote all these letters, it's clear that I should go to B first. But on your picture, actually, that's not clear at all because you can't tell. All you did was like put these arrows here, but there's no sense of the sequencing of the arrows. So don't do it like this. Here's the art lesson. How can you draw this in a way which makes it clear what you're actually talking about? I'm just going to erase those arrows. I have the original graph again. You can redraw the picture maybe. Don't do it like I just did it. Do it like I'm about to do it. How can you make it so that it's clear where you're going? The trick is you got to be a little sloppy. So what I mean by be a little sloppy, when you draw your line, your path, don't actually hit the vertices. Don't go through the vertices. Go nearby them. So here's how I am always going to write a path like this. You start at A. Of course, you can make it hit A when you start. But then I go to B next. So I'm going to go sort of next to the original edge. Then go to C. You see that? I did not actually go through the vertex B. Now, of course, everybody knows what I meant by that. I'm being a little sloppy here. I missed the vertex. The reason I want to be sloppy is because, as you saw last time, if you drive straight into there and then go straight out, it's impossible to tell after the fact which way you were actually going. All right, anyway, now C to A. I'll draw like that. And then A to D. Again, I am not going to actually touch the vertex. This is just a little art lesson here. Then D to E. So I'll go down here like so, right? Not actually touching the vertex on D. Then E to B, okay, up here. Then B back down to E, apparently using this edge because we're not supposed to repeat the same edge twice. And then E up to C, okay. Again, I did not actually touch that vertex. And then C over to D. And then D back up to A. And there is one edge left that I can use to go back up to A. All right. And finally, I hit A. Okay? This is very clear where the path goes from step to step. All right? So if you want to indicate your Euler circuit, you know, if this were a homework problem and I just said, show me an Euler circuit, you could write out the list like this to describe your circuit, or you could draw some kind of diagram like this to describe your circuit. And either way is fine. If you're going to draw the picture, which is usually easier to draw the picture, make sure you do it in a way that is readable after the fact. This one does have an Euler circuit. Let's talk about one that doesn't have an Euler circuit. All right, I think it's pretty clear that this one does not have an Euler circuit. Does not have an Euler circuit. Why not? Well, for instance, if we started at A, we could try A. Now, if you start at B, if you start at A, it must go to B next, right? Then I got two choices. I guess let's just say I went to C next. But then you'll be stuck, right? You're not allowed to use any edge more than once. You could try to go A, B, C, but then stuck, right? That doesn't work. Or is it because I went that way that was a bad choice? Well, no. If you went the other way, it's the same thing happens, right? Or A, B, D. Again, you get stuck, right? There's nothing special about starting at A. Is it any better if you try to start at B? No, actually, it's worse. If you start at B, you can go out to one of these things, but then you're stuck, right? So a graph that looks like that definitely does not have an Euler circuit. This is an easy example, but a larger graph can be much more difficult to understand if it has an Euler circuit or not. But I'm here to tell you, it turns out there's a very simple way to tell if a graph has an Euler circuit. And And if you know this trick, you will be able to tell more or less immediately. If I show you a graph within 5 seconds of looking, you have to know what to look for, but you will be able to tell. There's no calculations that you have to do or anything fancy like that. It's very obvious. So we're going to talk about Euler proved a theorem about this. Remember, a theorem is like a true fact in mathematics that can be proved. So Euler proved a theorem about when they exist and when they don't. Can I just say about this, right? When you look at a graph, you can tell immediately, if you know the theorem, if there is an Euler circuit or not. Now, there's a bit of language that is used in the theorem that I want to talk about. Mathematical language you're going to see in the theorem. This, actually, what I want to talk about for the next few minutes has nothing to do with graphs specifically. This is just a bit of language that mathematicians use all the time. And you may have heard of this phrase being used in your other math classes. I messed it up already. The phrase is if and only if. This is a phrase which is used by mathematicians mostly, or ordinary people don't say this in ordinary speech, but it's not a complicated idea, but it's a very specific idea that I want to talk about. So when you say if and only if in mathematics, this means that two statements are equivalent. Like logically equivalent. So if I say, and this if and only if you've seen this before in other math classes, you probably know this people generally write, just so you don't have to write that whole thing out, if with two F's. When you see this, if with two F's, it means if and only if, and this actually is different from the word if. They have different logical meanings. This is actually stronger than the word if. Anyway, it means two statements are equivalent. So for instance, if I say x if and only if y, this means that x and y are logically equivalent. And what that means is, I'll say i.e., if x is true, then y is also true. And if y is true, then x is true. They both have to be true. So when you see x, if and only if y, your interpretation of this should be, if x is true, then that means that y is also true. And if y is true, then that means x is also true. In other words, x and y, they represent the same thing logically. Either they are both true or they're both false in all cases. They are equivalent to one another. All right. I just wanted to get a good handle on using this phrase, if and only if. Let's just go through a bunch of very simple examples of what if and only if means and what it does not mean. How about this? Can we do a bunch of true or false? True or false? I am 35 years old. If and only if I am old enough to vote. Right? In the United States, you got to be 21 to vote, which is a little old in my opinion, but whatever. I'm not in charge. Anyway, the statement here says, I am 35 years old, if and only if I am old enough to vote. Is that true or false? What I want to get at is, am I correctly using the phrase if and only if or not? The answer is false. These two things that I'm saying here, we've got to compare this one here and this one over here. Are they logically equivalent? If I say I'm old enough to vote, is that the same as saying I'm 35 years old? And the answer is no. If you say I'm old enough to vote, it doesn't necessarily mean that you're 35 years old, right? You could be many different ages. You could be younger than 35. You could be older than 35. Now, it is true, if I am 35 years old, then I am old enough to vote. That's true. But the other way around is not true. If I'm old enough to vote, it does not necessarily mean that I am 35 years old. So this one right here, I'm going to put a big X on it. This is an improper usage of the phrase if and only if, right? Because these two things are not logically the same. One of them follows from the other, but not both ways. Okay, here's another simple example. How about this? I have seen the Statue of Liberty. If and only if what? Extra if. If and only if I have been to New York City. All right, Statue of Liberty, everybody knows, is in New York City. Is this a correct usage of the word if and only if? I have seen the Statue of Liberty, if and only if I have been to New York City. What do you think? Yes or no? Is that actually correct to say or not? The answer is... This is a wrong usage of the phrase if and only if. All right? You have to think two ways. If I've seen the Statue of Liberty, does that mean I've been to New York City? Yes, maybe. I mean, actually, you can see the Statue of Liberty from outside of New York City, right? If you can see it from like parts of New Jersey, can't you? So even that's not really true. But anyway, the other way around is definitely not true. If you have been to New York City, that does not mean that you've been to that you have seen the Statue of Liberty, right? You can go to New York City without seeing the Statue of Liberty. So this, if and only if, is false. Maybe one way of this is true, but the other way is definitely not true. All right. How about, here's one more. Oh, look at this. My marker's working great now. My name is Mark Nemec. If and only if I am president of Fairfield University. All right, right now, as I record this video, the president of Fairfield University is a fellow named Mark Nemec. Is this a correct usage of the phrase if and only if? My name is Mark Nemec. If and only if I am president of Fairfield University. What do you think? I'll give you a moment to think about it. This one actually kind of depends. Certainly, you have to think both directions of this. How about, is it true that if I am president of Fairfield University, then my name is Mark Nemec? That one is true because there's only one president of Fairfield University. And his name, it really is Mark Nemec. What about the other way? If my name is Mark Nemec, then I am president of Fairfield University. I suppose this would depend if there are other people named Mark Nemec, and I don't really know if there are. So can I just say, probably there are not other Mark Nemecs, but I don't know. I suppose I could have looked this up, but I didn't because I wanted to talk about the details here. So I will just say this depends if there's other Mark Nemecs. Right? If there was another person named Mark Nemec who was not the president of Fairfield University, then this would be false. But if that guy is the only Mark Nemec, then this one really would be true. All right. Does this give you some feel for what if and only if means? It really means that the two things are the same. Not like they're somehow related in some way, but they really are the same. So being Mark Nemec is really the same as being the president of Fairfield University because there's only one guy. I mean, maybe. I don't actually know. How does this look in a mathematical context? In a mathematical context, you use if and only if when you are describing two different ways of saying the same thing. So typically it would be used when you're saying something like this. X is even if and only if x plus 1 is odd. Right? This is a true fact. If you have an even number, if x was even and you add 1 to it, then the result will be odd. And the other way is also true. If you have something where x plus 1 is odd, then that automatically means that x is even, which means this is really true. So this if and only if statement is true. And you should feel like the interpretation, mathematically at least, is on either side here. These things that you're saying, they mean the same thing. If I told you that x is even, that's the same as saying that x plus 1 is odd. I mean, it sounds slightly different, but when you think about it logically, they mean the same thing. They both mean that x is even. Or you could say they both mean that x plus 1 is odd. All right. What would be interesting is, let me just say that mathematically deep statements look often, yeah, I mean, this is not always the case, but often look like something like x if and only if y, where x and y sound different, right? See, this is what I wrote here, x is even if and only if x plus 1 is odd. That's not terribly deep because everybody knows that like even and odd as concepts, they kind of go together. Right? And if you say something about something being even, probably you can rephrase that as saying something else about something else being odd, right? Because even and odd are very similar notions. They're kind of opposites, but they are both talking about sort of the same idea. Sometimes, though, you can encounter mathematically deep statements in which they say make this kind of relationship between two ideas which don't seem to be related at all, or they sound like completely different ideas. What this means is that someone has somehow realized there is a deep and true relationship between things that don't actually seem on the surface to be related at all. This is what mathematicians identify as deep statements, and sometimes this is what we call beautiful statements. Especially mathematically beautiful statements will say something like x if and only if y, where maybe one of them is a very complicated thing and the other thing is a very simple thing. We regard that as deep and beautiful because it reveals that certain things which seem to be complicated are actually very simple. Or it could reveal that something which seems to be very simple is actually very complicated. And these are the kinds of things that we like to explore. Anyway, I think we're ready. That was all just a warm-up to get you used to this phrase, if and only if. I think we're ready for Euler's theorem about Euler circuits. And here it is. This is the trick I said before. If you know what to look for, you can look at a graph and immediately say if it has an Euler circuit or not. Here's the theorem that Euler proved. We'll talk next time about why this is true, but I'll just tell you the theorem, and then we'll look at a quick example. Here it is. A graph has an Euler circuit if and only if every vertex has even degree. That's it. This is what Euler discovered. So I regard this as a deep and beautiful theorem because this concept here is, at least on the surface, a very complicated notion. It involves, if I just show you a graph and ask you if it has an Euler circuit or not, it's not clear at all how to answer that question. But this concept is very simple, and you can look at a graph and immediately verify whether this is true or not. It means if you want to know if there's an Euler circuit or not, it's the same as checking simply if every vertex has even degree. So, for example, how about this example that I drew before? The A, B, C, D, E. Remember this one? Does it have an Euler circuit? Now, it does. We know it does because I showed you one before, and I even drew the path. But you can check the degrees. Check the degrees. Are they all even or not? I put a question mark. Exclamation. Check the degrees. If they are all even, then there is an Euler circuit. If they're not all even, then there is not. And what are the degrees? Remember the degree? There's a vertex here also. The degree is just how many edges hit the vertex. So here, what's the degree? Count how many edges are going into this dot. 1, 2, 3, 4. So the degree there is 4. This one here, degree is also 4. Actually, all of these, the degrees are 4. And the one in the middle, the degree is also 4. Okay, they're all 4, which is, I suppose, a little interesting, but more importantly, they're all even. That's what I want to talk about here. All degrees are even. So there is an Euler circuit. And we already knew there was because we wrote it down, but I'm trying to show you how to use the theorem. All degrees are even, so there is an Euler circuit. How about one where there's not? How about this Mr. Plow example? Is there an Euler circuit or not? This one is not as clear when you're looking at it to tell. Can I actually hit every edge once without repeating edges? Check the degrees, right? Is there an Euler circuit? Check the degrees. This one. Remember, I'm looking each time for how many edges go into each vertex. All right, can I write down? This one has 2 edges, 1, 2. This one has 3, right? 1, 2, 3. This one has 2. By the way, when you're counting the degree here, make sure you count every edge. You might feel like this is a straight line going through this vertex, so it only counts as once because there's only like one line going through. No. You count how many individual edges are going into this vertex, and there are 3. 1, 2, 3. All right. How about here? Also 3. Actually, these points in the middle, they're all 3, and these points on the corners, they're all 2. Right? And the point in the very center of the square is a 4. Okay. Anyway, what I'm looking for is, are any of them odd? The answer is yes. The 3s are odd. So I'm going to say it has some odd degrees. So there is no Euler circuit. All right, you can tell very easily if there is or is not an Euler circuit by just looking at the degrees, right? Next time we'll talk about why the theorem is actually true. It seems kind of too good to be true. It really is true though.